Young's law is obeyed on ideal solids only, that is, solids that are both atomically smooth and chemically homogeneous. On regular daily life materials, the situation is quite different. This can be seen by inflating and deflating a drop on a common plastic. We see that up to some volume, the contact line remains pinned while the angle increases, until it reaches a maximum value where the drop edge starts sliding. This experiment shows that the apparent contact angle is not unique, and we call advancing angle its maximum static value. Conversely, when the drop is deflated, the line remains pinned down to a minimum value, generally much smaller than the advancing angle, and called the receding angle. Hence, the contact line on a solid generally ranges between two significantly different values, a phenomenon known as contact angle hysteresis. In the movie, advancing and receding angles were respectively 90 degrees and 30 degrees, showing that hysteresis, 60 degrees here, can be as large as the mean value of the angle, 60 degrees also. Angle hysteresis is responsible for drop pinning in many circumstances, for instance, as seen with rain on tilted windshields or vertical window panes. Contact angle hysteresis arises from the presence of defects at the solid surface, roughness on the one hand, and chemical heterogeneities on the other hand. Solids are not ideal, as we assumed when we derived Young's equation. So if we know the defects at the solid surface, can we calculate advancing and receding angle? The answer today is no. It's very difficult to take into account the correlations between these two defects. This sounds a bit frustrating. However, we can get a feeling about the variability of contact angles by considering simple elementary macroscopic defects. For instance, we start with a solid which is of a given hydrophilicity, characterized by a contact angle θ1, and this solid suddenly gets a different chemical composition, and this part is more hydrophobic with a contact angle θ2. Very naturally, when we push a liquid to the frontier between the two regions, we guess that we can have any angle between θ1 and θ2 at this particular point. So, indeed, the fact that we have something heterogeneous naturally generates a variability for the contact angle. The situation is quite similar when you consider a defect such as a groove on the solid. So the solid is flat, and at a microscopic scale, so I cannot see it with the naked eye, I have something like a groove like this, and it comes back here, but I will only consider the tip of this groove. So, because now it's chemically homogeneous, there is a single contact angle locally, which is θ1. I would get the same angle on this part, but because I cannot see the groove, I consider always the horizontal as my reference. And again, when the liquid is pushed to the tip, I can observe any angle between these two values. And if the angle of the kink here is denoted as phi, the variability of the angle here is between θ1 and pi minus phi plus θ1. As an example of that, we can consider a very common experiment we perform several times per day, which is filling and looking at a glass filled with water. So we have this glass. I assume that the glass is clean so that water wets the glass. So contact angle is very close to 0. And we know that we can fill completely the glass so that at the top we see an apparent contact angle which is 90 degrees, and we can even overfill the glass so that the apparent contact angle seems to be close to 180 degrees. But the top of a glass is a very special place. And if I make a close-up of this top, I see the inside of the glass coming to the outside of the glass, and when water is coming, below the top it is like this, just at the top it makes this apparent contact angle, and I overfill the glass and I get this shape. And this is exactly what is predicted by my formula, because in this case phi is 0, and our formula indeed predicts a very large interval of possible angles at the top of the glass, because angle can vary between 0 and pi minus phi, which is 0, plus theta 1, which is 0, which is pi.
A famous case where contact angle hysteresis plays a role is the so-called coffee stain effect. When we look from the top of an evaporating drop of coffee, we notice that the solid suspension colouring of the coffee gradually concentrates at the edge of the drop. Evaporation is more efficient close to the contact line where the liquid forms a wedge. Hence, water is constantly driven from the centre to the periphery, entraining the suspension to the contact line where it adheres to the substrate. This accumulation of grains anchors the contact line so that the receding contact angle, which had initially a finite value, tends to 0. Hence, the drop edge can remain pinned until the complete evaporation.
In this experiment, we place a water drop with a volume of 100 microliters on plexiglass. Water partially wets plexiglass with a contact angle close to 60 degrees. When we tilt the substrate, we see that the drop slightly deforms but does not move until the inclination reaches a critical angle close to 30 degrees. Then, the leading edge of the drop is at the advancing value, while the trailing edge takes a receding angle. If we repeat the experiment with a smaller drop, the volume is now 50 microliters. Even if we tilt the solid to an inclination of 40 degrees, the drop remains stuck on the substrate. On the other hand, if the drop is larger, with a volume of 200 microliters, it logically starts to move downwards at smaller tilt. This experiment evidences the balance between gravity and pinning, and it constitutes a convenient way for determining hysteresis. How can we understand this phenomenon quantitatively? We are going to follow here the model proposed in the 60s by Firmage, which is a very classical model. So we have this tilted substrate, and we consider as a tilt angle the angle at which the drop will depart, and we call it alpha. On this slope, we place a drop, and we noticed that this drop is asymmetric, making an angle at the front theta A, which is larger than the angle at the rear theta R. When we make this little sketch, we immediately notice that curvature is not constant, that curvature is higher at the leading edge, so that there is a gradient or a difference of Laplace pressure between both edges. Pressure being larger where it is more curved, the force, the capillary force, which arises from this difference of angles, is such that it can indeed oppose gravity. Once we say that, we can express a typical difference in Laplace pressure between both edges. We consider a 2D system, or if you prefer, we consider the drop as if it were a ribbon perpendicular to the blackboard, in which case the difference of Laplace pressure can be expressed as surface tension divided by a typical size of the drop times the difference between the cosines of these extreme angles. And this can be balanced by gravity, the difference of hydrostatic pressure between both edges, which is on the order of rho g r, rho being the density of the liquid, and r, the typical size for the drop, times sine alpha. So what we get is a relationship between the tilting angle, which is a measurable quantity, and the size of the drop, times the hysteresis. We find that at departure, the sign of alpha is given by the square of a length which only depends on the liquid, which I call LC. It is the so-called capillary length, which will be discussed later, divided by the size of the drop to the square times the difference between the two cosines. Two cases. Either we are on an ideal solid and delta cosine theta is 0, in which case alpha is 0. We indeed expect that if there is an opening, a drop will move for any slope. If now we are in a more common situation where delta cosine theta is on the order of 1, then we find two different limits. Either the size of the drop is very small compared to this capillary length, which is typically millimetric, in which case the drop will remain stuck for any slope. And this is a very common case. When we look at raindrops on vertical window panes, we know that very generally they are stuck. If now R becomes large compared to the capillary length, then there is always an angle, which can even become very small, for which we'll observe the motion of the liquid. So we understand the physical meaning of this typical length, the capillary length. It is the length above which, very generally, gravity effects will dominate surface tension effects. In addition, we see that Fermit's formula allows us to determine very conveniently the contact angle hysteresis from the measurement of alpha. For a given liquid, the capillary length is known because the square of the capillary length is surface tension divided by rho g, and of course the size of the drop is known, so that we can very simply measure this important quantity by this daily life experiment.
Drops on regular planar inclines only flow when their size is a few millimeters, a consequence of contact angle hysteresis. A solution for generating an anti-adhering surface consists in impregnating a microtextured material with oil. If the texture and the oil are carefully chosen, a drop of water will remain at the top of these lubricated materials. This nearly annihilates pinning and the resulting angle hysteresis, as seen in this movie, where tiny drops are found to be highly mobile. Such materials can be used to design gliding surfaces on which not only water, but also highly viscous and non-Newtonian liquids, such as mayonnaise and ketchup, will easily flow without leaving any trace behind. Phalaropes are seashore birds living in Arctic regions that use fluid dynamics at different scales for fishing. Firstly, they move in circles, thus inducing a flow inside the cold water, which brings microorganisms to the surface. Secondly, they pick twice per second drops with their beak and then succeed in transporting these drops, containing the food, to their mouth. This is one case where contact angle hysteresis is beneficial. As seen in this artificial beak, the movement towards the mouth is triggered using a mandibular motion. The drop being asymmetric, closing the beak makes its leading edge move before its trailing edge. Conversely, opening the beak makes the trailing edge move before the leading edge. Hence, the drop can travel with a very limited amount of energy.